In this talk, we present SLAM, an efficient dense visual SLAM system based on implicit representation of signed distance fields. Recent neural rendering-based SLAM systems like IMAP and NiceSLAM have produced high-quality geometry but lack traditional SLAM methods' efficiency. Our proposed method reduces this gap by introducing novel techniques to improve computational efficiency, and it achieves superior results compared to state-of-the-art methods. Our method outperforms NiceSLAM in terms of geometry and appearance quality when tested on real-world scenes. Our approach utilizes a multi-scale triplane representation and shallow decoders to predict the sign distance field and color for each 3D point. These predictions are then used to render pixel depths and colors using an SDF-based volume rendering technique. A dense visual SLAM method involves constructing a 3D map of an unknown environment while simultaneously approximating the camera pose. To achieve this, the SLAM model reads RGBD frames with unknown camera poses in a sequential manner and incrementally reconstruct the scene representation. As new input frames are provided, the model updates the current estimation of the camera pose in the 3D scene. This allows for real-time mapping and tracking in a 3D environment. Let's take a closer look at the inputs and outputs of our method. The inputs are a set of sequential RGBD frames represented as IND. The outputs consist of camera poses and an implicit truncated sign distance field representation denoted as phi-g. This TFDF can be directly used with the Marching Cubes algorithm to extract 3D meshes. We expect the TSDF to indicate the distance to the closest surface with a positive sign in the free space and a negative sign inside the surfaces. Specifically, we employ normalized TSDF that is 0 on the surfaces and has a magnitude of 1 at the truncation distance t. Here you see our proposed pipeline. Since our representation for geometry and appearance is symmetric, we show them simultaneously in this figure with a star placeholder. We use triplane representation at coarse and fine resolutions. We cast rays from the current camera pose estimation and randomly sample points along them. Each point is projected onto feature planes, and the resulting interpolated features are added together for coarse and fine planes separately. We form the final feature for each point by concatenating its coarse and fine features. We use shallow decoders for both geometry and appearance that convert point features to TSDFs and colors. Our SDF-based volume renderer takes these predictions and renders pixel depths and colors. Specifically, we use stratified and importance sampling to sample points on array. We query TSDF and raw color for each point and convert TSDF to volume density. We then use classical volume rendering to render depth and color of a pixel. For optimizing scene representation parameters and camera poses, we use 2 per-point loss functions and 2 rendering loss functions. The per-point losses are applied to each sample point individually, while the rendering losses are applied to sample rays. Our free space loss encourages the points between the camera pose and the truncation distance to have a TSDF of value +1. We encourage the sample points in the truncation region to follow a sign distance field approximated by the depth map. We also impose consistency between the rendered depth and colors with the ground truth ones. We compare our method against state-of-the-art neural rendering SLAM methods, IMAP and NiceSLAM. Here we show the geometry reconstruction quality on the replica dataset. As the results show, our method better preserves the details of a scene and generates fewer artifacts. Furthermore, we evaluate the accuracy of localization and tracking on the ScanNet dataset. Our approach demonstrates superior performance in following the ground truth camera trajectory. Here, we visualize frame-by-frame comparison of reconstruction and localization quality between our method and NiceSLAM on a scene from the real-world ScanNet dataset. We outperform NiceSLAM in both camera tracking and scene reconstruction. Finally, we provide a runtime comparison between our method and existing approaches. This analysis indicates that our method runs significantly faster and is more efficient in terms of model size growth rate with respect to the scene size. Thank you for visiting our website for additional results and the implementation source code.